In this video, we're going to do a few more examples involving sequences. So remember, a sequence is a function whose domain is the set of positive integers. So the inputs of your sequence, so you usually have a formula giving the nth term, and the terms start at 1. So each integer you plug in gives you the next term. So it's a list of numbers that exhibit a pattern. So we did some examples of finding the terms of a sequence. So here would be the formula for the nth term. So that's Bn. So if we wanted to find B3 or B5, we just have to plug in the different n values. Okay. Now there's one here, so we want the first 5 terms of this C sequence. So we're going to want to do n equals 1. Okay, so n equals 1. So C1 is going to be -1 to the 1 plus 1. So that's -1 squared, which is +1. Okay, and then we have C2. So this is where n is 2. Okay, that's going to be -1 to the 2 plus 1. So that's -1 to the 3. So that's going to be -1. And then we continue like this. So C3 is when n is 3. So that's going to be -1 to the 3 plus 1, which is -1 to the 4. Any even powers of -1 give +1. So not C5 yet, C4 is -1 to the 4 plus 1. So -1 to the 5, which is -1. And C5 is going to be -1 to the 5 plus 1, or -1 to the 6, which is +1. So our sequence, okay, the first 5 terms are going to be 1, -1, 1, -1, and 1. And then it keeps going like that. Okay, so that's a fairly easy pattern to recognize. So recognizing the pattern is actually the harder part. So if I give you a list of numbers and you want to try and find the formula for the nth term, this is not that easy. So the example that we did earlier was sort of an easier example. Part B here is a bit harder. So if I think, okay, this one goes with input 1, this one goes with input 2, input 3, input 4, input 5. Okay, so then you might be thinking, okay, so how do I get from 1 to 3? Well, I could multiply by 3. Okay, now if I multiply this by 3, I also get to 2, so that's lucky. Okay, now if I multiply this by 3, I get to 9. Okay, so not 11. So multiply by 3 isn't going to work. Okay, so I want to think of something else I could do. So these are not all odd numbers. Okay, this one is even. So that's out. So we could be thinking, okay, if I square the number, so 1 squared is 1. Okay, so if I add 2, I could get to 3. So now 2 squared is 4, and if I add 2, I can get to 6. 3 squared is 9, and if I add 2, I can get to 11. 4 squared is 16, so if I add 2, I can get to 18. 5 squared is 25. If I add 2, I can get to 27. So it seems like that I could get to each term by taking the square of the input and then adding 2 to it. Okay, so there's probably other ways that you could write this as well. Okay, this is one way that works for those first 5 terms. Okay, so now we had recursive sequences. So here you define a sequence in terms of the previous terms. Okay, so we did one example. Let's try another. So here I have U1 is 1 and U2 is 1. And then to find UN for n bigger than 2, I take the one before and the one before that and add them together. Okay, so the first 5 terms, I might do more than 5 actually. So U1 is given, that's 1. U2 is also given, that's 1. And then U3 is going to be u2 plus u1. So that's going to be 1 plus 1, so that's 2. u3 is going to be u2 plus u1. Okay, so that's going to be 2 plus 1. Sorry, this is u4. So it's going to be u3 plus u2. Okay, but that is 2 plus 1. So that's 3. u5 is going to be u4 plus u3. So u4 was 3, u3 was 2, so this is 5. And if I did u6, it would be u5 plus u4, so it's going to be 5 plus 3, which is going to be 8. Okay, and it just keeps going like that. Now this is a special sequence, okay? It's called the Fibonacci sequence. So you might have heard about these. Okay, so the Fibonaccis are very famous. They're in some movies. So as n goes to infinity, the ratio of the terms approaches what we call the golden ratio, which is this number here. Okay, now the closed form formula for the nth term is very complicated. So it's hard to determine. You need tools better than what we have. So in the example previous, we could find the closed form one because we knew what was happening to each term, okay, in that way. So that it was just a factorial, but it's not always easy to find the closed form formula. So sometimes you can't do it in our class anyway. You need higher tools. So that's the Fibonacci sequence. So you just keep going by adding the two previous terms together to give you the next term. So then we also talked about summation notation. So if you want to add up a bunch of terms in a sequence, then what you can do is you can use this sum. So this is a capital sigma in the Greek letters. It represents a sum in math. So the bottom thing here, k is the index. So notice that the formula has a k in it. So k is going to range from 1, the starting point, to n, the finishing point. Okay, and we did an example of that. So here's another example. So here we want to try to write this using summation notation. Okay, so I'm going to rewrite, so that they all look the same, the number 1, I'm going to write as 1 over 1. Okay, so this is what my sequence or my sum looks like. Now, you might notice that the bottoms are consecutive odd numbers. Okay, so how you can write an odd number is you can write it as 2 times some number. Okay, 2 times a number always gives you an even number. And then if you just add or subtract 1, you're going to get an odd number. Okay, maybe I should have used that m as a k because that's what we're going to use in our formula here. So you can add or subtract a number. So depending on where you want to start. So because we want to start at 1, so we want this to be k equals 1, k equals 2, 3, 4, 5, etc. We want to subtract 1. Because when k equals 1, this is going to be 2 times 1, which is 2. Okay, so 2 times 1, and then, so we don't know if it's plus or minus 1, but we want it to equal 1. Okay, so the only way to equal 1, if I take 2 and I subtract 1. Okay, because 1 is what we start with here. So that means I could write this as 1 over 2 times 1 minus 1, and 3 is 2 times 2 minus 1, that's 4 minus 1. 5 is 2 times 3, so 6 minus 1. And you can see how you can see the inputs, right? So 1, 2, 3, etc. I'm not going to do 7 and 9, but now for 19, 19 is 1 less than 20. So this is going to be 2 times 10 minus 1. And this one here is going to be 2 times 11 minus 1. So 22 minus 1. Okay, so I have k equals 1, k equals 2, k equals 3, and this one is going to be k equals 10 and k equals 11 because this input here is our k value. Okay, so then I could write this using the summation notation. So I start at k equals 1 and I go to 11. And I can write it as 1 over 2 times k minus 1. Okay, now if you wanted to add 1 instead, you could just start at k equals 0. Okay, so this is the same. Okay, so if you started at k equals 0, so depending on where you want to start, then it would go to 10, and it would be 2k plus 1. Okay, that does the same thing. So it just depends where you want to start. I decided I wanted to start at k equals 1, and that's why I needed to do the minus 1. But that's how you can get the odd numbers. So that is how we can write that as a sum in 2 different ways, in fact. Then we had some properties for sums. So if you have a constant times your sequence, you can pull the constant outside the sum and multiply it after. Okay, so this is a constant multiple rule. If you're adding two sequences together inside your sum, you can actually do each sequence sum separately and then add after. Similarly, if you're subtracting 2 sequence sums, you can do them separately and subtract after. These ones are a bit different. So if you want the sum from m to n, you could go from 1 to n and then subtract all the terms you don't want. So that's 1 to m minus 1. The reason we might want to do that is because these formulas that we have for these particular sums that we use all the time, they always start at k equals 1. Okay, so that's why these things here might be easier to compute than that thing there. Okay, so that's why you might want to use that. Okay, these formulas we're going to be using a lot when we're computing sums because we can break down a lot of things into a constant, a single power, a square power, or a cube power. Okay, and then we know how to compute those sums. So we did a couple examples, okay, but let's do this example here. So I want to break it down. So I can split it up. So this is k equals 1 to 52 of 2k squared minus the sum from 1 to 52 of 40k minus the sum of 5. Okay, now I can break it up even further because I can take out the multiples. So the 2 can come out, and then it's the sum from 1 to 52 of just k squared. Oops, this is a minus. Okay, and then that 40 can come out, and it's the sum from k equals 1 to 52 of just k. The 5 could come out, but I'm going to leave it in because we have a formula for a sum of a constant. Okay, now these, so this sum, I know how to compute using this formula. Okay, this sum, I know how to compute using this formula. And this sum, I also know how to compute using this formula. Okay, so I'm going to be using those. So when I have the sum of k squareds, so my n is the finishing bit. Okay, so it's n plus 1, 2n plus 1, all over 6. Okay, so this is going to be 52 times 52 plus 1 times 2 times 52 plus 1, all over 6. Okay, now when I sum of k's, That's n times n plus 1 over 2. So that's 52 times 52 plus 1, okay, all over 2. And then the constant is just the constant times n. So it's going to be 5 times 52. Okay, so then if I add these up, so this number simplifies to 48,230. And then this is minus 40, and this number is 1,378 minus 260. And if you compute that, you get 41,080 total, I think. So that would be how you could compute that sum. So you just want to break it apart into pieces that we have formulas for. So that's an introduction to sequences.